So this video is meant to show you a little bit extra about the Gibbs free energy and help you out with some of the definitions and the calculations. So the first thing that you want to know is, again, Gibbs free energy is talking about spontaneity. And spontaneity, you can see here by the definition, there are a number of different things that you might be looking at. For example, a person who is spontaneous is somebody who does things maybe at whim. So perhaps they're the kind of person who happens to see butterflies and goes around catching them. Or maybe they hear of a great adventure and they want to go and see what that's going to be like. Whether it's a person who's acting spontaneously or maybe a process that's behaving spontaneously, it always happens without any sort of stimulus, so any sort of external encouragement, or it happens involuntarily. Like you breathe spontaneously. You don't have to always remind yourself to breathe. So if we have a chemical reaction that's considered spontaneous, we're referring to the fact that the reaction occurs without any external help. So you don't have to force it to occur. It's not like, like a mouse in a wheel running and running and running to keep the wheel going. The wheel just goes automatically. So that's what we're referring to with a reaction that occurs without any external help. A good example of that in lab that you've seen is going to be reactions like a Bunsen burner. Once you ignite it, it just keeps burning. Non-spontaneous, therefore, is a reaction that requires some sort of assistance. And so maybe that means that you have to physically continue to add a chemical. Maybe it means that you have to plug it in order for it to work. Maybe it just means that you've never seen it react because that particular reaction is not spontaneous. All right, so as with enthalpy and entropy, we also have a state function in Gibbs free energy. Again, these are similar, like they're related concepts, but they don't actually interfere with each other or cause each other. There's no causal effect here. Enthalpy, remember, is heat. It's going to be your thermal energy. Entropy is chaos. How does it behave? What does it look like? And Gibbs free energy is now going to be your spontaneity. Does it actually react all on its own? So when you're calculating it, one great way of solving for it is by taking your Gibbs free energies and solving as if it's a reaction. You'll notice that on your blue data sheet, you happen to have a series of Gibbs free energy of formations. And again, they're formations because they represent how much energy does it take to create that substance. So does it actually require you to make that substance by doing things to it? Maybe you need to pressurize it. Maybe you need to greatly heat it. But you have to physically be doing something. Because those are listed on your table, those formations will still be taking products for this equation and then going through and subtracting the sum of all of the reactants. There are some benefits to this equation, and there are definitely some disadvantages. First off, the benefit is that it's the exact same format of equation as enthalpy and entropy has. The downfall is that really this equation is meant to be at 25 degrees Celsius, so what we would consider lab temperature or standard conditions or room temperature. Because of that, you're really only going to be able to use this equation for that one particular temperature. All right, we're going to go ahead then and pull out your blue data sheet, if you haven't done so already, and take a look at this calculation. So the first thing you want to notice is that our reaction has not yet been balanced. So we need to do that first. Let's go ahead and put a 3 in front of the ZnS and a 1 in front of Sb2S3. That will give us 3 in front of zinc and a 2 in front of the Sb. And I apologize that I forgot the line right there. All right, we happen to be at 25 degrees, and that's how you're going to know you can use this equation, as opposed to the next one we'll be talking about. All right, as we go through, again, you're going to be looking for changes in Gibbs free energies. In order to look at this as a whole reaction, we're going to start out by solving for the 3 Gibbs free energies of formation for zinc. We then want to include 1 of the antimony sulfides. Oh, let me rewrite it this way. We're then going to go ahead, now that we have all of our products listed, doing our reactants next. So 3, again, because of the coefficients being the number 3. We're going to be looking for formations of zinc sulfide, and we'll include 2 formations of Sb, which is called antimony. All right, so as you turn to your sheet, again notice we're alphabetical, so this is the front side. We're going to want the next page, and we're going to scroll around. So the first thing that I remember is that I needed zinc solid. Here's my zinc solid. And notice that as I go across for zinc solid, I have 3 numbers. Again, keep in mind that the third number is going to be Gibbs free energy of formations. So we can see here that zinc is going to have a value of 0. All right, next up, we're going to look for the antimony sulfide. So Sb2S3, here it is. And again, we want the third number, so a negative 174. All right, those are all of our products. Now let's start looking for reactants. We want 3 zinc sulfides. So here's our zinc sulfide as a solid, negative 198.3. And we're going to add to it 2 of the antimony as a solid. And our antimony is here. Oh, we've got 2 different kinds. We don't want the gaseous antimony. Make sure you're grabbing the solid antimony, and that one happens to be 0. Okay, so now that you have all of your variables filled in from your table, you're just going to go ahead and calculate. So remember again, watch your signs. That's going to be the thing this unit that's going to mess you up, if anything. And so as we calculate this, I am getting a positive 420.9. And again, if I look, just double checking on my table, I can see that Gibbs free energy was kilojoules per mole. And since we did just multiply by each of the coefficients, we know that it's going to not be kilojoules per mole, but rather just kilojoules. All right. So a couple of things about that. Again, keep in mind that because we're talking about spontaneity, things that are spontaneous are going to have delta G's that have a negative value. And things that are non-spontaneous will have delta G's that are in fact a positive value. As we look at our answer below here, we happen to have a positive value. So that means that this reaction does not happen unless you somehow force it to happen. You will not see this reaction occurring in nature. What do you notice about the delta G formations for all of the various elements? As we saw here with the zinc solid and the antimony solid, which was here, if it's the natural state of the substance, the formation of delta G will in fact be 0, very much like the enthalpy is 0. So as long as it's an element at their natural states, they will all have formations for Gibbs free energy that are 0 in the amount of work, right? The spontaneity of it. It's not spontaneous or non-spontaneous. It's already been formed, and so the work will in fact be 0. So that's another good tip. So some great things to notice from this. Again, what are your sign conventions? Right there. And also, what is your Gibbs free energy of formations for anything that is an element? All right, let's go ahead then and turn the page. As we turn the page, what you're going to notice is very simply we've got one more box, because what happens if you are not at standard conditions? So this infers that you are not at 25 degrees Celsius. Any other temperature is going to work. This is actually the equation that you want to be using as you're using your lab. When you use this equation, what you do is now we're going to see how the 3 variables interact with each other. Again, they don't dictate how each behaves, but they do impact what's going to happen. As you take a look, this is going to be delta G for Gibbs free energy. It's being set equal to enthalpy, so the change of heat for the reaction, minus the temperature, and this will be the temperature in Kelvin, multiplied by delta S, and that's the entropy, so how much chaos is in the reaction. Okay, so let's practice that. Again, this is great because you can use it for any temperature, including 25 degrees Celsius. So I know a lot of students just default to this equation because it's a little less work as long as as long as you already have the enthalpy and entropy variables. All right, as we take a look at our question, this very first example, notice again, we're going to take our Gibbs free energy, and we're going to solve by plugging in my delta H. Now, the one thing that I want to do before I start really plugging in is, am I all in the same unit? So these both need to be in kilojoules or joules. As long as they are equal to each other, that's all you need. So we've got delta G. Again, we're going to plug in our heat. So here's a negative 1,599.6 kilojoules. And we're going to subtract the quantity of temperature. So this temperature, again, you need to be in Kelvin. So 273 plus the 75 makes it 348 Kelvin. And you're going to multiply that by the negative 0.02972 kilojoules per Kelvin. As you do that multiplication, notice what's going to happen to the Kelvin. It's this one here for temperature, and it's in the denominator, so we can go ahead and cancel those. And now order of operations. We're going to multiply this first. And again, if you're just typing it into your TI Inspire, just make sure that you are plugging it in correctly. So this value is going to end up being negative 10.34 approximately. And we're going to end up taking these two values, and the negatives will cancel each other, so we'll add. All right. Again, as I mentioned, with respect to significant figures, you want to kind of fall in the area that things are falling. So if I look, there's a lot of decimal places here for my entropy. There aren't any for my temperature. There's about 1 decimal place here. So I should be somewhere around right between 5 significant figures, 3 significant figures, 4 significant figures, somewhere between 3, 4, or 5. This unit is hard to dictate your significant figures because you're pulling variables that are considered standards off of all sorts of tables. So if you get confused with significant figures, try to just stick with 3 or so. Excuse me, so if you were going to go ahead and put a negative 1,590 kilojoules, that's totally fine. Again, the goal being that you're not putting in every single digit that your calculator is giving. You don't need to give them all. So there's our value right there for Gibbs free energy. And again, just showing you how to use that equation. It'll now be up to you to determine whether you want to calculate with the first equation for Gibbs free energy, which again would be at 25 degrees Celsius, or the second equation for Gibbs free energy, which can really be for any temperature that you'd like. All right, so this video is going to end here, and if you'd like more practice, there's going to be a couple of other videos for you to try out, or just use as a supplement as you work through the problems.